Also, if all the presenters from the spotlight can come to the first row, that would be great.
Just a little bit, so it should be fine, but it's chopped up a bit. 1080p? Yeah? We're testing. Yep.
Spotlights number 3, 4, and 8, please come to the front.
So where's the timer going to be? It's going to be on the ground? Maybe you can push it somewhere. It's hard to see. That's better. For me, at least. I don't know about everybody else.
We are going to start the session. We are still missing the spotlight presenters 3, 4, and 8. Please come to the first row. Good morning, everyone. My name is Fernando de la Torre. I'll be co-chairing this session in analyzing humans in images. Today we have a very exciting 3 oral presentations related to image synthesis for makeup transfer, age progression, and also improving face detection of tiny images. All of them are extensions of GANs. And then we are going to have also 8 spotlights where half of them are going to be also related to GANs. So it's going to be a very GAN-centric session.
Hi, everyone. Welcome to the session. I'm Ira Kemelmacher from the University of Washington on Facebook. So each talk will be 12 minutes, and then we'll have 2 minutes for questions. So if you want to ask a question, please come to the microphones in the middle of the room and ask it away. All right.
And with that, we will start the first talk of the session, which is Finding Tiny Faces in the Wild with Generative Adversarial Networks, presented by Bernard Ghanem.
All right. Thank you, Fernando. All right. So on behalf of the postdoc who actually did all the work, Yancheng, I'm going to be presenting this talk. He wasn't able to make it this CVPR, unfortunately. So I'll try to do my best after an 11-hour flight to give you an overview of what the method's about and any technical details that you need answered. He's the ideal person to talk to. So the age of detecting faces that are large and frontal and controlled settings is over. We have really good solutions to do that. But nowadays we're dealing with images like this, where the faces are small, they can have different orientations, scale, and inclusion, and so forth. The problem is much more difficult, obviously, for all these different reasons. So the scale, I mean, they could be big or small faces, the pose could be different, there could be occlusion, and so forth and so on. So the problem is much more difficult when you get into the wild. What we're going to target in this paper is the scale problem. Basically, we're going to target faces that are very small. And by that, I mean they could be as big as 10 by 10 pixels. So this problem is still a challenge for face detection in the wild. The reason why is that most methods out there, most detectors out there, especially deep learning-based ones, they downsample their feature maps to represent these faces. So a face image of 10 by 10 pixels can be represented by a 3 by 3 feature or even smaller. So a lot of structural information is lost, and therefore your detection performance is degraded, and you get a lot more false positives. So this is the scope of this paper. So what have people done in the literature to try to alleviate that? Well, they use the age-old technique of image pyramids. So you take the original image, you downsample it, you upsample it, and you search this exhaustively, the scale of faces. So large ones in the upsampled versions and smaller ones in the downsampled versions. Obviously, in the upsampled versions of the original image, it can help you in detecting maybe tiny faces. The smaller versions don't help you much. The problem with this approach is that it increases computational time because you have to search over the different levels in the image pyramid. And, of course, the GPU memory also increases. Can we do something else to alleviate this problem? What other people have done is also they've zoomed into the different patches in the upscaled images. And as you can see, they use some traditional, for example, bilinear interpolation methods that don't really preserve any of the facial structural information that's useful in classification. So you get a lot of false positives in this case. This is where our method shines. So basically, we're proposing a unified network, a framework, that can be added onto a face detector so that you can be able to better detect and classify these tiny faces. So we've proposed a GAN-like framework here where you have a generator network. Its goal is to super resolve these tiny images. So instead of using bilinear interpolation, you use something smarter. You super resolve that we're using an upsampling network, and you refine it by to maintain the fine details using a refinement network. Those images are then discriminated using a discriminator network that outputs whether this image is a face or not, and whether it looks realistic or not. So let's delve into the details of this network. The input is an image from the wild. Our goal is to find all the faces of all orientations, all scales, and all under all different illuminations and blurring. The second step is to apply a off-the-shelf face detector. We use our own, the MBFCN, this multi-branch, fully convolutional network. That's in our archive paper, but you could basically use any detector that you want. What it does is it outputs localizations of where faces are and where non-faces are. These outputs are used in training and in test. Once you have these patches in the image, you feed them into this generator network. This generator network is made up of a super resolution or upsampling network first, and that's fed in to be refined by a refinement network that does some deblurring and some denoising. Then once these super resolved images are produced, they are fed through a discriminator network that figures out whether these, which is trained to figure out whether these image patches are super resolved or actually high resolution. So it figures out whether they're real or fake, just in the same way traditional GANs do their work. Also, they output a probability of whether that image, a super resolved image, is a face or not a face. So that's the architecture, but how do we end up training this kind of architecture? So basically it's a combination of a GAN kind of loss with a super resolution loss together. So the overall objective is made up of 3 terms. The first term is an adversarial loss, a traditional one that you see in GANs. Basically, it makes sure that the generator produces images that are realistic looking. So they should be realistic looking in comparison to the high resolution images of those patches that we have. This loss is agnostic to whether it's a face or not. This loss is a traditional, again, reconstruction loss used in super resolution to encourage the generator to generate super resolved images that look realistic. This is, again, agnostic to whether it's a face or not. The third loss is where the face information comes into play. It encourages the discriminator to output whether this super resolved image is a face or not. By minimizing all these 3 terms together, basically we encourage the generator network to produce realistic-looking patches that are super resolved, 4 times the size of the original patch, and they maintain fine details of the faces that make it easier for us to classify them in the final stage. So, of course, following conventions that are used in GANs, we use alternating optimization to update the weights of the generator and the discriminator in an alternating way. I won't go into details of that. You can come to the poster afterwards. So once we have this network trained and we want to evaluate how well it does and whether our design choices were accurate or not. So we're making use of this wider face dataset. It's the most challenging face dataset out there so far. It contains about 400,000 faces in general. Half of them are in testing. It contains a variety of poses, scale changes, illumination, and so forth, all the types of nuisances that happen in the real world. And it's broken down into different subsets, easy, medium, and hard. And these are correlated to the size of the faces. So the bigger faces are the easy ones. Once they get smaller, they become medium. They become part of the medium subset. And the hard subset are basically where the tiny faces are. So we're going to see a bunch of ablation studies to validate the choice that we did for our network and our loss function. So first and foremost, does this generator network help in detection? According to this graph, yes, it does. So it improves the AP results by about a couple of points, across all the subsets. So basically, as compared to the baseline detector, which subsamples the feature maps and therefore produces more false positives, what our proposed method can do is super resolve these tiny faces and allow for better classification in the hard subset as well as the easy and medium, because even the larger faces, they can make use of super resolution. What if we just remove that refinement network altogether, the one that was supposed to maintain the fine details of the faces? Well, we can see that there's a dip in AP if we remove it. It gets affected the most in the hard subset where the faces there are smaller. So refining these small faces is very important. You need to make sure that your fine details of the faces are preserved. And here's an example of what I mean. So the first and third rows are inputs. They're the outputs of the baseline detector, and they're the inputs to the generator network. As you can see, the second and fourth rows are the outputs of the generator network. What it does is basically it super resolves these images. The details are preserved. You could see the eyebrows, eyes more obviously now. And these are kind of structural features that are made use of in the classifier to distinguish between faces and non-faces. What about the loss? Do we need all those 3 terms? Well, what we did was we just dropped the individual losses and see what happened. Well, if you drop the adversarial loss, the one that encourages that the generator network produces realistic-looking image patches, we see a drop in performance, obviously, because without it, the generated images are blurry and noisy, and you go back to the original regime or the old regime of what used to be done before. If you drop the classification loss, also the performance goes down, and the reason why is that classification loss is encouraging the generator network not only to produce realistic-looking patches, but realistic-looking face image patches. So the fine details of the faces are preserved, which makes classification easier at the end and reduces false positives. So that's why the performance actually improves. Here's the overall evaluation on the wider face data set as compared to other techniques. So obviously I wouldn't be here if it didn't outperform the other methods. It does, especially the runner-up, the SFD detector, which used to be the state-of-the-art. The overall improvement is about 1% AP on this very challenging data set, which is significant. The majority of the improvement is on the harder subset, which is exactly why what our method is designed for. So the improvement is about 1.4% on the harder subset. To follow convention, we also compared against the smaller, more traditional FDDB dataset. We ranked second there as compared to SFD. I want to note here that the FDDB dataset has a lot of unlabeled faces in the test set. So even though you actually detect correct faces, you could get penalized because they weren't actually manually annotated. So in the SFD paper, they actually manually annotate 200 missing faces in the test set and add them to the evaluation, while we just reported results in the original dataset. If we had access to those manually added annotations, we would have gotten better results. I'm going to conclude with some qualitative results on some very complicated and challenging images. So here's one. The detection results are in red. The ground truth is in green. We get almost every single face in the image. The overlap between the detection and the ground truth is pretty significant, so we're getting them pretty tightly around the face. And the number of false positives is pretty minimal. Here's another example. We missed the ones in the background at the very far end here. Obviously, these are very hard. I mean, even as a human, it would be hard to detect these faces. You would have to hallucinate them. Here's another one, a classroom photo maybe. Here I want to just note that this framework of adding a GAN-based super resolution that refines and maintains the details of objects, small objects and images, this idea can be used in other tasks, especially generic object detection, and this could be seen as a future work of this work. Actually, we have submitted to ECV, so we'll see how that goes. And with that, I'm going to conclude, and I'll be at poster A7 in the poster session if you have any other questions. And I'm happy to take any questions that you have right now. Thank you.
We have time for a couple of questions. Please go to the microphone.
Hi, I have a question. If you're using a GAN to upsample the faces, it seems to me that this only enforces that the face looks like a realistic face, not that it looks like the original face. So I'm wondering if there's anything in the loss function enforcing that condition, and if this is something the authors thought about.
So basically in the loss that we have here, so remember there's a combination of three losses, right? So this loss is the adversarial loss that makes it look realistic. But this loss is an MSE loss of a reconstruction loss. So basically, we have a higher resolution version of the face itself. So it's not going to, for example, take a low resolution version of my face and then generate something that looks like Fernando's face, for example. This is part of the loss that does it. Yeah, he's more handsome than me, so it'll never happen. Does that answer your question? Thank you.
Two questions. The first one is, can you say anything about gaze? So does it preserve gaze and the direction which it's looking? Did you do any tests for that? Second thing is, how long does it take to process an image?
For the first question, I don't know if we did any explicit experiments for gaze, but again, with this MSE loss, I don't think it will change the gaze that much in terms of reconstruction. For the second one about the speed, it's in the paper somewhere. So it's at the poster for sure. So Thanks. Come over.
Chairman,
Anybody else?
I would like to ask, you're using the MBFCN detector to get like faces and non-faces. So how much is your GAN network sensitive to the error produced by your detector network?
That's a good question. So the ablation study, this one, the one where we tried it with and without the whole generative network, that shows that it's for this detector itself, it wasn't as sensitive. So what would be interesting is to use the same framework with other detectors and see how it's sensitive to the outputs of each detector. But for the MBFCN one, it doesn't seem to be as sensitive. Thank you.
All right.
Thank you.
Great. So the second talk of the session, learning face age progression. The presenter is Huang. Let's go.
Thanks for the introduction. We're glad to share our work on face age progression. Face age progression is to aesthetically render a given face image with aging effects. The same technique can also be applied in a reverse direction to rejuvenate faces. It has a wide range of applications. For example, forecasting facial appearance of young children, generating contemporary photos of missing individuals, entertainment, and so on. In recent years, this topic has received increasing attention, in particular from some top conferences. No slides? We go on from here. In recent years, this topic has received increasing. Okay. Sorry for that. In recent years, this topic has received increasing attention, in particular from some top conferences and journals. The same as in other computer vision tasks, we can also notice its development from handcrafted methods to deep model-based ones. Conventional methods can be roughly classified into three types: mechanical simulation-based, aging function-based, and prototyping pattern-based. In spite of some promising results, they have obvious limitations. The aging process is usually complex, the aging mechanism cannot be accurately formulated, and aging effects are not rich enough. More recently, deep generative approaches show their superiority. In CVPR 2016, the pioneer deep model for age progression is proposed, and it generates smooth intermediate faces by an RNN structure. In CVPR 2017, GAN is investigated for this issue, and the method tries to separate identity and age in the latent space for better results. In Multimedia 2017, the transition pattern discriminative network is proposed to regularize face aging rules, and skip layers in the generator are used to retain information at different levels. In ICCV 2017, the short-term age progression is modeled by short-term modeled by individual race night blocks, and the long-term synthesis is reached by chaining short-term stages. It doesn't require burdensome pre-processing, and only 4 landmarks are needed. Although performance is greatly improved, the two basic requirements, namely aging accuracy and identity permanence, are not perfectly handled in those deep learning methods. For example, sometimes the texture synthesized are not as old as we expect, and sometimes the identity information seems lost. Furthermore, we have further requirements. Synthesis is expected to launch on the entire face, including forehead and hair. Results are expected to be photorealistic. We try to skip complex pre-processing, for example, many landmarks. And we also try to avoid strong data assumptions. For example, aging sequences, or paired images of the same subject. So here are our motivations. First, we use the GAN framework since it proves effective in generating visually appealing faces conditioned on pre-images and doesn't require matching pairs of samples in training. Second, we address aging effect generation at identity Q preservation in a coupled manner. Third, we handle age transformation in a fine-grained way. Specifically, in the generator, we have a traditional encoder and decoder structure to achieve aging effects while simultaneously keeping person-specific information. Now, compound critic is employed. The first part is the age transformation loss, where both the actual young faces and the generated old faces are regarded as negative samples, while the true old faces are as positive samples. To make finer texture details, we propose a pyramid hierarchy to process facial representations at multiple scales. Here, we use the least square loss to replace the original negative log likelihood objective, which penalizes samples depending on how close they are to the decision boundary in a metric space, minimizing the Pearson chi-square divergence. Phi age is pre-trained for age estimation using VGG16. The second part is identity loss, measuring the input-output distance in a proper feature space. Here, Phi ID is the light version of the network of deep phase descriptor shared by the VGG research group, and D is the squared Euclidean distance. The third part is a pixel-wise L2 loss in the image space, and it is adopted for further bridging the input-output gap. The overall training loss of the generator combines three parts, and the loss of the generator is only L GAN D. In our experiments, we use three popular databases, MORPH, CACD, and FGNet. The key properties of these databases are summarized in the table. MORPH provides well-controlled samples, while the other two give the ones in the wild. As the number of subjects in FGNet is quite limited, our major experiments are carried out on MORPH and CACD. FGNet is only used for test in the cross-dataset evaluation. In pre-processing, we only need to detect the centers of the two eyes. There are four types of evaluations: visual fidelity, aging accuracy, identity permanence, and comparison with the state of the art. Here, I would like to highlight another contribution of this work, different from previous studies, which mostly use subjective evaluations. We add comprehensive, objective ones, making the results more convincing. First, we see some results on the MORPH database. More results on CACD. From this picture, we can see some details of our results. Our method shows a high robustness to occlusions, pose changes, and glasses vary. The aging effects are clear in all major facial parts: forehead wrinkles, eye bags, mouth corner sag, deepened laugh lines, and even beard and hair. At the same time, we can see that the person-specific cues are preserved, as in the yellow circles. To analyze age accuracy, we conduct objective evaluation by using the age estimation API of Face++. The upper figures are the results of the synthesized faces on MORPH and CACD, while the bottom ones are the results of actual faces on the two databases. As we can see, the clusters of synthesized faces of individual age groups are very close to the ones of actual faces. For identity permanence, we use the face verification API of Face++, comparing face pairs between test faces and synthesized ones, or between synthesized faces from different age groups. The verification rates are quite good at a very low false alarm rate, indicating identity information is well preserved. We also compare the results of the one pathway structure and the pyramid architecture to validate its contribution. Here are the results on MORPH. The proposed method outperforms the single pathway in both subjective and objective evaluations. The case is similar on CACD database. Finally, we compare our results to the state of the art by crowdsourcing. 10 volunteers are invited for pairwise comparison. 1,380 votes are made in total, and around 70% favor the proposed method. Now, I'm concluding the talk. A novel GAN-based method for age progression is proposed, which addresses aging effect generation and identity cube preservation in a coupled manner. The discriminator of the pyramid architecture is presented to enhance the synthesized age accuracy, and more convincing experiments are conducted. Thanks for your attention, and more discussion is welcome at poster 18. Thank you.
Questions and also spotlights, please come to the front.
I have one question about the generalization of this network. I think it can be seen as a sort of controlling the attribute by intensity. So why did not you apply to other attributes like smile, bang, bored, or blonde hair? Does some problem or difficulties exist?
Not exactly. Actually, the generability of the method is tested on the FGNet dataset in a cross-dataset manner, where we train the model on CACD and directly test it on the FGNet. And we can see from the result, very good performance is achieved. And you talked about some other attributes. Actually, we generate the results for all the photos in the dataset. But due to the limited space, we cannot show all the images.
Maybe I'll ask another one. So in your results, you show that a person that had a beard is going to stay with a beard, or a person that had glasses in some point will stay with glasses.
Yes.
Can the aging algorithm find a way to, people change glasses and people change beards and remove beards and so on?
Yeah. Actually, this is a question, but in our case, we try to keep the original context of the input image. So we don't change the glass or some other clothes. We try to keep the original thing. Okay.
Are you ready?
Yes.
All right, let's thank the speaker again.
Now, Huiwen Chang will present the last oral presentation of the session. She's going to show us how to render virtual makeup automatically.
So Thanks for the introduction. Next, I will present a system called PairedCycleGAN for asymmetric style transfer to automatically stylize spaces. So our original goal was to apply the makeup to a source image based on a reference style, and a desired result is shown on the right. So given different styles, the results try to match them while keeping the face identity. Because it is hard or impossible to find an image triple that includes the source reference and the ground truth, so it is challenging to train it using supervised learning. And previous work solved the problem by defining the style and content loss in feature space to optimize the output. And one state of art considered the style transfer as an image analogy with weak supervision. So, given these two input images, it will output a pair of images that exchange the style appearance of the input pair. However, those general style transfer work tend to distort the edges, which could be necessary or fine to achieve the artistic style. But applying them directly to styles such as makeup could lead to unrealistic results. So recently, there's works proposed to use generative adversarial networks to address the image domain transfer problem. For example, CycleGAN can transfer between the horse images and zebra images, but it requires two sets of images from each of those domains. But for our problem, as we mentioned, it is hard to collect different faces with the same makeup styles. So can we still adapt the makeup style transfer to image domain transfer problem? We could imagine that one domain will be faces without makeup, and the other domain will be face with makeup. But the problem here is that if we take this image as input, we don't know which of the output it will produce, because image domain transfer framework consider all of those makeup styles as one single domain. So user cannot specify which of the styles they would like the result to have. So here the fundamental problem is that unlike the functions transferring between zebras and horses, the transformation function between makeup and no makeup are not invertible. So let's make a comparison here. For all the previous work we just mentioned, such as deep image analogy or image domain transfer, when we consider both directions as the style transfer, their forward and backward functions are symmetric. In comparison, we define a new set of problem called asymmetric style transfer. Because our forward function is the makeup transfer, which require a reference for user to specify the look of the result, while the backward function, makeup removal, only requires one input. Because we assume that to remove one's makeup, it does not require another person's face as a guidance for what a natural face should look like. Another example of asymmetric style transfer is that transferring the patterns from a reference onto a white shirt. And backward function will be remove the patterns from the shirt into a white shirt. Again, the forward function require two images as input, while the backward only need one. Next, let's look at our pipeline. We take two images as input, the source and the reference, and which we collected from YouTube makeup tutorials. And during training time, we learn a generator G associated with a discriminator, which try to distinguish whether an image is realistic image after makeup. Note that this image with the red border is our final output for makeup transfer. At the same time, we learn a backward generator F and a discriminator for the domain of the natural face without makeup. After this stage 1, the output pair by G and F exchange the styles of appearance of the input pair. Therefore, as we run the generator one more time, the style should exchange back. So the ideal output in the stage 2 should look exactly the same as the input images. So we define our content loss as the distance between these two images because we hope that if we remove the makeup from our final output, it should look exactly the same as the source images to keep the face identity. Then we also define our style loss as the distance between these two images, because we hope that the result can be faithfully, the style can be faithfully preserved from the input to stage 1 and from stage 1 to stage 2. So this is our pipeline. Note that F only takes 1 image as input, while G takes 2. So some of you may wonder whether we can also allow the style removal generator F also take a pair of images as input. Let's call it H. Then the setting will become the one for symmetric style transfer. If so, the constraints on the functions will be too loose because many functions could possibly satisfy such constraints. One possible example will be, given the input image pairs, G can always output the first input image and H can always output the second. They can simply fill the discriminators and can also minimize the loss functions, but they are obviously not what we desired. Therefore, we only consider asymmetric style transfer problem and only allow F to take 1 image as input. During training, we found that when G finds a point that can fill the discriminators, it refused to change much to better match the reference style. So we can see that here, the output looks similar with each other, despite the reference style are totally different. Actually, it is a known problem because GAN has this tendency to collapse to a set of parameters, which is only a subset of the desired distribution. We originally hoped that we can avoid this problem by having this style loss, which is the distance between the reference and the output in stage 2. But however, L1 is only good at capturing the difference in low frequency, so it is not enough to prevent this GANs collapse problem. To simplify the problem and let it focus more on high-level details, we first add a phase passer and train the multiple transformation functions for each phase segment. You may notice that our segments are in this circular shape with the skin tone padding, because it is for adding the random rotation in order to augment our data. To enable G's output better match the reference style, we tried to add another discriminator for whether two faces have the same makeup. Our first attempt is inspired from our training process, because that during training, we observed though the output in stage 1 is not similar with the reference makeup, but it's consistent with the output at stage 2. So we used the output from the stage 1 and stage 2 as the positive examples for our style discriminator. Though it helps sometimes, it's still not robust for a stable training. So instead, we try another strategy for the style discriminator. Because detecting phase key point is relatively easy, so we warp the reference makeup to the source phase with Poisson blending, as shown on the right. Though the phase does not look like either the input images or the reference phase, it does give a hint that what two images with the same makeup style should look like. So we use them as the positive examples of the style discriminator. And here are the output of our final results with the style discriminators we just mentioned. And as you see, they match the reference style much better and produce more various makeup. For the architecture, we experienced with different ones such as UNet and WarpNet, and more details could be found in the papers. But in general, we found that UNet performs poorly when transforming styles from smaller eyes to larger eyes or faces with different expressions. So instead, we use dilated ResNet because dilation can enable large receptive field without downsampling the features. And ResNet can help shuttle the low-level features from the shallow layers. We train the delta images instead of the output directly to enforce the output that has the same skin tone with the source image. For evaluation, we conduct a user study on Amazon Mechanical Turk to compare the output of different methods. We ask Turker which one matches the reference better, and our results are preferred in 72% of the time compared with the state-of-the-art. An accessory application is the makeup removal function learned by F. We compared with a recent makeup removal paper. Both of the methods produce natural-looking face, but our networks remove the makeup more aggressively and generate sharper results. So one limitation is that our function cannot reconstruct realistic blemishes or wrinkles based on our assumption and our training data. We have demonstrated the performance on makeup transfer applications. We also experiment with the framework on other applications such as face aging and object style transfer. And here are some preliminary results. And finally, we show an example running on a video. And thanks, everyone, for listening.
We have time for a couple of quick questions. I would like to know a little bit how well it generalized to different type of makeups. So how many type of makeup do you have styles in the training set?
So we collected our makeup data set from YouTube makeup tutorials, and it includes thousands of makeup styles we extracted from the frames in the YouTube videos.
Okay.
Yep.
Also, you have done processing locally in the eyes and in the mouth. How do you ensure photorealistic results at the end by doing locally synthesis in the eyes and in the mouth?
We then used pulsar blending to blend all the parts together, and we didn't use another discriminator for faces. Yeah.
So with this, we'll conclude the oral session, and we'll start with the spotlights.
While we're setting up, so each spotlight is 4 minutes. There are no questions, but feel free to come to the posters.
That's the middle of the video. That's not the beginning of the video. It's not correct. Yeah, we can try that.
Yes, that's correct. Nice. Okay, hi. We found a conceptually extremely simple method to improve pose estimation by using unlabeled data. So, but let me first tell you about what is the final task. So we have given a single depth image, and we want to estimate the pose of the hand. This is usually given by 3D positions of the joints and fingertips, and we want to learn this estimation using a model. So we want to learn a model to do this, right? And of course, you know, if you want to learn such a model, you need a whole lot of training data, and all this training data needs to be labeled, and the labels need to be in 3D. And of course, this is pretty difficult to provide for real data, a huge effort. So it would be much more efficient to learn from unlabeled data, and that's actually the goal for this work. And our idea is actually based on a really simple observation, namely that the pose is predictive for the appearance of the hand from any viewpoint. So if you know the pose, you can imagine how the hand would look from any other viewpoint. And this is only based on the pose and shape, a rough shape. So, but for our work, we don't know the pose because we want to learn from unlabeled data. And but what we can easily do, let's say, is to capture a second viewpoint. So to take a second camera, capture a second viewpoint, and reformulate the problem. Instead of trying to estimate the pose, try to predict the second view. And during the learning process, what should pop out as this kind of side product is a pose representation, right? So what we are doing is, like, from the image, from one view, we learn a model to predict a latent representation, and from this latent representation, we are learning a second model which should predict the appearance of the hand from another viewpoint. And if this second model is able to do this, the assumption is that the latent representation on which it is based has to capture really specific information about the pose. Right? Has to encode pose-specific information. And then, of course, we can train this whole thing end-to-end, add some labeled data, train it in a semi-supervised manner. And if we do this, we see that we can reduce the error by quite a bit, or also reduce the labeling effort by 1 to 2 orders of magnitude at the same level of accuracy. You can find details in the paper or come to the poster. But one last thing I wanted to show you was some investigation of the latent representation space. And what you can, of course, do, for example, is, or what we did, for example, was to look at the nearest neighbors in the latent space. So you use some validation samples, you project them to the latent space, and then you search for the nearest neighbors in the training set. And if you do this for our method here on the right side, you see that all the nearest neighbors for a query sample exhibit a really similar pose to the query sample. But if you do it for the latent representation of an autoencoder, this doesn't happen like that. It's just a comparison on the left side. And yeah, this should indicate that we have learned something really pose-specific using unlabeled data. So I hope I motivated you to check the paper or come to the poster, even better. Yeah, thanks.
Hello everyone, my name is Hao-Shu. Today I'm going to introduce our work on weakly and semi-supervised human body part parsing. We all know that pixel-level human body part parsing is important to human understanding. However, labeling the part-level, pixel-level semantic segmentation is effort-consuming. On the other hand, there are already a large number of available key points annotations. So we are wondering whether it's possible to exploit the key points to facilitate the task of part segmentation. And our answer is yes. Our idea is to exploit the anatomical similarity among humans to transfer the parsing results of some labeled instances to an unlabeled person. For a person with key points annotations, we find his or her nearest neighbors in the human body part parsing dataset based on key point similarity. Here we show an example. For the person on the left, we find persons with similar poses in the parsing dataset, and we show the corresponding parsing labels here. Based on human key points, we calculate the affine transformation matrix Q of each body part between two persons and use it to get the morphed part parsing labels for the unlabeled person. Here we show an example. After affine transformation, the morphed part parsing labels fit the unlabeled person better. Then we average these morphed results to get a part level prior. Here we show more results of our part level prior. It can be regarded as the possibilities of whether a pixel belongs to a specific body part. After getting the part level prior, we refine it based on local image evidence to get the fine parsing label. We use a fully convolutional network to do the refinement work. It can generate high-quality parsing results. The training pipeline of our refinement network will be detailed during our poster session. Here we show some examples. We can see that after the refinement network, the parsing results are good enough now. Here we show some results of the final transferred labels using our method. These results are used as extra training data for the task of body part parsing. With our semi-supervised method, we outperformed the fully supervised baseline by 6 MAP, and our result achieves the state-of-the-art. Next, we show some qualitative results. And some result in complicated crowdsourcing. And that's it. Thank you. Our poster session is at B11, and our model and source code is publicly available now. Thanks again for your attention.
Okay, good morning, everyone. I'm Zhang from Peking University. Okay. I will introduce our work, Person Transfer GAN to Bridge Domain Gap for Person Real Identification. Okay. This is a joint work of PKU and the UTSA. First of all, let's see the performance boost of Person Reality in the past 10 years. So you can see that some recent algorithms in our community has actually performed better than human. But we have to say that Person Reality is still far from being solved. So why? Let's see two comparisons. The first one is between the real-world data and our existing academic datasets. So you can see that our existing dataset cannot simulate the real difficulties because they have a small scale, fixed things, short time span, and fixed lighting condition. So to push forward research, we need a more realistic dataset with larger scale, more complex things, and longer time spans. Another comparison is between the test data and the training data. Because it's very expensive to annotate human ID, our training data is always limited and cannot cover the real-world distribution. So we need better data augmentation to solve this problem. Actually, we can use annotated data on another dataset to solve this problem. However, this is not simple. For example, when we train on CUHK and test on PRID, we only get 2% rank-1 accuracy. So it's very low because different dataset has different lighting backgrounds, camera parameters, and so on. So there exists a domain gap between datasets. And to make this data augmentation more effective, we need to bridge the domain gap. So in our work, we basically do two things. The first is we propose a more realistic dataset called MSMT17. It is collected by simulating the real scenarios. So we have 15 cameras, both indoor and outdoor, and totally have 180 hours of raw videos, and covering 12 time slots in 1 month, and including the morning, noon, and afternoon. And we use fast RCN for person detection, and the annotation takes 2 months, resulting in 126,000 bounding boxes and more than 4,000 identities. Okay. This is a comparison with existing dataset. So you can see MSMT has the largest size, very complex things, complex backgrounds, multiple time slots, and complicated lighting variations. Okay, another thing we do is we propose a PT-GAN to bridge the domain gap. The goal is to transfer the training data on dataset A for training on the dataset B. So in PT-GAN, first we transfer the style like the backgrounds, lighting, and so on. Meanwhile, we keep the identity information unchanged. Okay, this is a comparison between PT-GAN and the CycleGAN. So you can see that both of these two models can transfer the style, but the PT-GAN can preserve the identity information unchanged. And this is very important for model training. This is an example of transfer CUHK to PRID. So to Duke, sorry. So you can see that after the transfer, the background has changed, but the identity information is not changed. This is another example of transfer market to Duke. So PT-GAN can bring significant performance gains. So on PRID, it can improve for more than 300%. Okay. So this is the end of this brief introduction. And we make two contributions. The first one is MSMT dataset, a more realistic and challenging person-ready dataset. And another is PT-GAN, an effective algorithm for dataset transfer. Okay. So both the code and our dataset has been released. You are welcome to download and try, and welcome to our poster. Thank you very much.
Hi, my name is Adrian Spur. I'm from the Advanced Interactive Technologies group at ETH Zurich, and today I'd like to present our work on 3D hand pose estimation. So what's the problem our paper tackles? Given a monocular RGB image of the hand, is shown on the left, we would like to infer its 3D joint configuration. Here ground truth is shown in the middle, and our prediction is shown on the right. This is a challenging task, as self-occlusion and a lack of depth information makes inferring the three-dimensional layout of the hand difficult. The first to tackle this was Timon and Brox, who constructed a pipelined approach, lifting 2D key points to 3D. A more recent approach is by Mueller et al., which we'll be hearing afterwards. They jointly regressed the 2D and 3D joint coordinates and fine-tuned their predictions with the help of skeletal fitting. We, on the other hand, assumed the existence of a low-dimensional manifold of biological, plausible hand poses, which we would like to learn. Samples that do not lie on this manifold are not valid hand poses. An example of this can be seen on the red dot. Similar assumption has been exploited in model-based hand tracking with depth images. This raises two questions. Can we learn this manifold from data? And is it consistent across input modalities? It turns out the answer to both questions is yes. To do so, we learn a statistical hand model represented by a single cross-modal latent space with the help of variational autoencoders. we can embed hand data of any modality into this latent space. Here, each color corresponds to one data modality. Using the latent space representation, we can then retrieve the 3D joint configuration. Specifically for the task of 3D hand pose estimation, we can embed an RGB image into this latent space, obtaining latent space sample Z, and then predicted 3D hand pose representation. Due to the generative natures of VAEs, we can also reconstruct the input image given the same sample Z. Since the latent space can be trained on multiple modalities, 3D pose can also be predicted given a depth image. As mentioned before, our architecture makes use of VAEs that naturally extend to cross-modal training to learn a unified hand pose latent space. Most precisely, a set of encoders Q take data sample X in the form of RGB, 3D, or depth images, and project them into a lower dimensional manifold. A set of decoders P reconstruct the hand configuration in any modality. During training, each modality alternatively contributes to the construction of this shared latent space. The cross-modal training results in a unified latent space. This can be seen by visualizing it via t-SNE and comparing training the VAEs separate, as seen on the left, versus training them unified, as seen on the right. Again, each color here corresponds to one input modality. Cross-training results in a unified embedding space of the samples, whereas when training individually, each modality has its own manifold. You've already seen results on the real data. Here are predictions on the more difficult rendered hand pose dataset. Again, blue being ground truth and red our predictions. Our model works well under difficult conditions such as low lighting and self-occlusion. With minor modifications, our model achieves competitive performance on depth data as well. Due to the latent space, we're capable of generating new, consistent data sample pairs of physical, plausible poses. This shows that our learned manifold is consistent with respect to the different data modalities. Here's a preview of quantitative results. Left and center plots the percentage of key point error. We outperform related work from the time of submission on old tested RGB datasets. Additionally, due to the shared latent space, our architecture is capable of performing semi-supervised learning. The accuracy plot can be seen here on the right. For more details, I'd love to have a chat with you at my poster, B17. Thank you very much.
Hello, everyone. I'm Li Qian Ma from KU Leuven. Our paper is Disentangled Person Image Generation. Our motivation is to learn image generation model for person images that explicitly represents the foreground, background, and the pose. The task is to synthesize the person images while independently controlling the three factors. Our model can be learned in a self-supervised way, which means we do not need any paired training data. How to do this? We first disentangle the person image into the three factors and then combine them together with the reconstruction pipeline. The previous pixel-to-pixel paper deals with the image-to-image translation problem with the conditional GAN, and then the CycleGAN extends it into an unsupervised method with the cycle consistency constraint. Both of them focus on appearance transfer. Then the PG square network provides the explicit body structure transfer for person image. It is learned in a supervised way. We propose the framework for both appearance and structure transfer, and our model can be learned in a self-supervised way. We have two stages. In the first stage, we learn the embedding feature space with the reconstruction pipeline, and it is the self-supervised way. Then in the second stage, we only train the mapping functions from the Gaussian space to the learned embedding feature space, so that during testing, we can sample the embedding features from the Gaussian noise, and then decode the features to the images. We do the sampling in two stages. Why? Because the person image is very complex, and it's not easy to sample the images from the Gaussian noise. Now let's see some results. First, the sampling results. The top part shows the result on the person identification dataset. We can sample the foreground, background, and pose separately or jointly. The bottom part shows the results on high-resolution deep fashion dataset. We can sample the novel clothes styles and person pose from the noise. One interesting experiment is inverse interpolation. We first use the gradient descent to find the corresponding Gaussian code in the Gaussian space, and then we do the linear interpolation in the Gaussian space. We can inference the reasonable interframes between two real images of the same person or different persons. As to the person identification dataset, we can control the disentangled three factors. We fix the foreground and sample the background and pose to get different images of the same person, so that we can generate a virtual dataset. With this dataset, we can benefit the unsupervised person identification task. As to the person pose transfer task, our self-supervised method can achieve comparable performance compared to the supervised method, PG square network, and we can generate more realistic images. Given the sequence of the target pose, we can also do the person video generation. Here we show the results of cross-person pose transfer. That is to use the person B's pose to drive person A's appearance, and vice versa. If you are interested in our work, please come to our poster at B20. Thank you.
Hello everyone, I'm Adrian, and today I'll present our work on integrated fashion landmark localization and super resolution of real-world low-resolution faces. I will start by offering a brief overview of the problem at hand, building up on previous work. I'll then continue by presenting our main contributions and the key results. Simultaneously super-resolving faces and localizing facial landmark is a chicken and egg problem. On one hand, being able to detect the facial landmarks has already been shown beneficial for face super-resolution. On the other hand, if one could effectively super-resolve low-quality and low-resolution faces across the whole spectrum of facial poses, then facial landmarks can be localized with high accuracy. Traditionally, methods for image and face super-resolution consist of a generator trained with a L1 or L2 pixel loss. However, this usually produces blurred images. Recent improvements include the addition of a perceptual loss and a GAN loss that makes the generated images more realistically looking. In this work, we propose to improve face super-resolution by introducing a novel structural loss based on a face alignment network that has the role of enforcing a structural and pose consistency between the target and the low-resolution input image. A byproduct of this is that the employed face alignment network also works well for low-resolution images. The newly introduced heatmap loss tries to minimize the difference between the prediction of the face alignment network made on the ground truth high-resolution image and the one produced by the super-resolution network. In practice, this helps preserving the pose and the expression better. The entire network is trained end-to-end in a jointly manner. In terms of PSNR and SSIM, our network provides competitive results when compared against SR ResNet. We note, however, that PSNR and SSIM are known for not necessarily reflecting the perceptual quality improvements. Here, some results on bilinearly downsampled images are shown. Notice the influence of the introduced heatmap loss that makes the overall facial structure more consistent. This is especially noticeable around the mouth, nose, or the eyes. Because PSNR and SSIM are often not representative, we additionally propose to measure the quality of a super-resolved images in terms of how well a pre-trained face alignment network performs on the super-resolved images. We found that face alignment accuracy correlates well with the perceived quality of the faces. Our results show that our novel loss significantly improves the performance across the whole range of facial poses. We also tried our method on real-world low-resolution images taken from wider face. We note that, to our knowledge, this is the first time that such setting is evaluated. The results of our method can be seen in the last row. Notice that our method largely outperforms SRGAN when retrained using the same data and setting. Here are shown some qualitative results on face alignment on low-resolution images, where the predictions are overimposed on the input 16 by 16 pixel images. Notice that our method can produce high-quality fittings for the whole range of facial poses and expressions. That being said, in this work, we propose a novel heat-map structure loss with the aim of improving the performance on both face alignment and face super-resolution. We have shown that our method produces state-of-the-art results on both tasks. Thank you for your attention, and please feel free to pass by our poster number C1 for more details and additional results.
Hi, I'm Wang from National Lab of Pattern Recognition in Institute of Automation, Chinese Academy of Science, and will present our work, multi-stage adversarial losses for pulse-based human image sensors. As we know, sensors are low-view human image is a very important problem. It can help to solve the cross-view vision tasks, for example, gait recognition and person ID. However, human image sensors is very challenging due to the huge variability of human posture, complex foreground and background. To keep human posture correct in all viewpoints, modeling human pose is a very natural choice. Moreover, adversarial learning is widely used in image generation due to the multimodal characteristic. So, in this paper, we propose a pose-based human image sensor method which can keep the human posture unchanged in all viewpoints. Furthermore, we adopt multi-stage adversarial losses separated for the foreground and background generation, which fully exploits the multimodal characteristics to generate more realistic-looking images. Our methods contain 3 networks for 3 stages. In the first stage, a pose transform network is proposed to synthesize 2D target pose of other perspective from the conditional poses. In the second stage, a foreground transform network is proposed to synthesize the target foreground image with 2D poses and conditional human foreground image. Here, an adversarial loss is used to improve the image quality. In the third stage, a background transform network is proposed to generate the full image with the conditional image and the generated foreground image. 2 adversarial losses are imposed to generate clear and detailed images. To verify the effectiveness of our method, we perform extensive experiments on the human 3.6 mm dataset. It can be seen that our method achieves the best performance in the 5th column, which keeps human pose the same as the inputs, and generates clear foreground and background images, while the other 3 state-of-the-art methods can't keep the pose correct in all viewpoints. We also generate the multi-view human images from a single image at intervals of 45 degrees. We can see that our method can generate high-quality multi-view human images. We also perform pose analysis and show the failure cases. On left figures, we input several pose parts into the proposed network to explore the role of 2D human pose. We can see that our method can generate human body appearance corresponding to these pose parts. On the right figures, we also show the several failure cases. The first row shows the case of occlusion of body parts, which makes our model very difficult to recover the occluded appearance. The second row shows the case of depth missing in 2D human pose, which leads to the depth disorder of body parts. It can be concluded that human pose is very important for human image synthesis, and multi-stage adversarial loss can help to generate high-quality foreground and background images. In the future, we will use human image synthesis to other visual tasks. Please come to our post for more details. The number is C4. Thanks.
We had some difficulties with the first spotlight. Franziska is going to try to present from her laptop, and with this, we'll conclude the session.
Okay, finally. Hello everyone, my name is Franziska and I will present our work titled Generated Hands for Real-Time 3D Hand Tracking for Monocular RGB. Our goal is to estimate the full 3D pose of a hand from an RGB image or video sequence. Let me give you an overview of our approach. We start from monocular RGB image that we feed to a CNN to regress 2D joint heat maps and root relative 3D joint positions. Then, we fit a kinematic skeleton model to the predictions to obtain a temporally stable and biomechanically plausible full 3D hand pose. Our whole tracking pipeline runs in real time at 50 frames per second. Note that both our 2D and 3D predictions are essential to obtain a robust global 3D result. The 2D joint heat maps enable us to recover the global 3D position with respect to the camera, since the relative 3D predictions do not contain this information. On the other hand, poses with the same 2D projection can only be distinguished by the root relative 3D joint locations. When using neural networks, there's always one big question, and that is, which training data did you use? We can record a lot of real hand data, but 3D annotation at scale is infeasible. Thus, previous work has used synthetic data, which gives you perfect 3D ground truth annotation for free. Unfortunately, there is a domain gap, which means models trained on synthetic data might not generalize well to real data due to a difference in features. Therefore, we propose a new image-to-image translation GAN to enhance our synthetic data such that it better mimics the features of real hands. We want to make sure that hand pose does not change during translation, such that we can transfer the annotation from the synthetic to our enhanced GANerated data. To enforce this, we propose a novel geometric consistency loss, which also gives the name to our network, the GeoCon-GAN. Here you can see some example GANerated hands that we further augment with various backgrounds to train our joint position regressor. Now you might ask, does GANerated data actually help when testing on real data? And I can tell you, yes, it does. We performed an ablation study on all sequences of the stereo dataset. We did not train with any data from this benchmark. We can see that adding GANerated data in yellow outperforms using synthetic data in blue or doing naive color augmentation in orange. We also compare to previous work. When using the standard evaluation protocol of the benchmark, our method, in orange, improves over all existing approaches, including the only other monocular RGB method by Zimmermann and Brox in yellow. Also qualitatively, we outperform Zimmermann and Brox, especially on more challenging datasets like EgoDexter, where their method, shown on the left, fails under occlusion. Since we only need monocular RGB video for our approach, we can apply it to community video as shown here. If you want to know more details about our GANerated hands, come visit us at poster B5 in the session now. Thank you.
All right, thank you so much. Let's thank all the speakers again. Thanks.